Antonio Marinelli. He got the physics degree here in Bologna with Professor Moscardini, and then he moved to Pisa, where he got the PhD in 2010. And he spent some year in Pisa, and then we spent 4 years in Mexico, where he worked with the high altitude water telescope. He is an expert in multi-messengers and high energy astrophysics, in particular on cosmic ray, gamma ray emission, high energies, and also neutrinos. Today, we talk about the recent discovery of neutrino emission from the CIFER. I stress the CIFER AGN-1068. I stress the CIFER because in the past there was a claim of detection of neutrino from blazar, but it seems that neutrino can be produced also in CIFER. AGN-1068 is a very complex CIFER, jet, starburst, there is everything in this galaxy, but it's very interesting. These results are very interesting. Please.
Okay.
Thank you.
Okay. Thank you, Paola, for the nice introduction, and I'm happy to be here and to discuss a bit, of course, about AGN-1068. And I will give also a brief introduction on the status of neutrino astronomy. So I hope not to be too boring for the people who already know all the last discovery in neutrino astrophysics. Then, so I will start. Sorry. Oh, okay. Sorry. That's okay. This work. Okay. Perché ho visto questo è sì. Questo non funziona? No. Ok, forse vado con questo. Ma non funziona? No, neanche qua. Sorry, there is a problem.
Meglio? Anche l'altro?
No, non neanche uno. Okay, this is okay. Yes, sorry for the interruption. Okay, so a brief introduction. So here I just put a multi-messenger sketch of what we have up to now, connecting the very energy neutrino. So the neutrino that we observe, in this case I reported the one observed by ISCO. I will not speak about the detector. So since everybody more or less known what is this kind of how this kind of detection works, and so basically neutrino from TeV range up to PeV range. So it's this is the range where we are focusing in this talk. And then we have here the diffuse component from Fermilab, and also the diffuse observation from ultra energy cosmic rays. In principle, as you see here, you have inside of this neutrino reporting sets, you have different components, and somehow it's interesting to see that the balance in energy, so the energy density between these three messengers are more or less equal. But it's important always to stress the fact that probably, and we know that looking at different messenger, as in this case, we are looking at different deepness in the horizon of where we are looking for. So that's an important information to keep on in this kind of study. So at the moment we have a diffuse flux that is a more than 10 sigma respect to the background that we have from the atmospheric neutrino that arrive also to the detector. And here I reported just some first 2-3 slides where I described how we can tell that a spectrum that we see in neutrino is somehow correlated with some astrophysical sources, so they have some astrophysical origin. And in particular, we have that the spectral energy distribution of this kind of signal that we see somehow follow a power law, and you see here the normalization of this power law versus the spectral index for different sample of reported neutrino from ISCO. And we know that in the acceleration of cosmic rays in the sources for Fermi first order, second order, we have this kind of expecting shape of the spectral energy distribution. And that's more or less the level of normalization that we have at 100 TeV for the measured spectrum. And also we have when we look at the arrival direction to this neutrino, is actually what we expect, since most of the signal come from the extragalactic origin. We expect that the signal should be somehow uniform in the sky. And as you see here, the distribution in the theta angle with respect to the iScope, you see that basically the only unhomogeneity basically can come from the fact that when you are looking to the other side of the hemisphere, basically the Earth start to be opaque for neutrino that goes above 100 of TeVs. And also another important information is that we are looking also to the different families of neutrino. And even though at the source production, we know that the distribution of the three families is not homogeneous, because this depends on the branching ratio on the production, and the fact that most, in this case, we are producing neutrino through ionic decay and to the kind of interaction that we have in the sources. So you can have a different distribution at the sources, but then what you will observe at the hair is something that is homogeneous between the three families. So this means that the origin of this neutrino is extraterrestrial, so means that they had enough space to oscillate between one family to the other. And then exactly what we observe is, you can see here the triangle between the three family. And so the best fit is very close to the center of this triangle. And then, of course, there is a speculation about the fundamental physics about on the region that we have this best fit, but we are not talking today about this. And so we can put together different information like the arrival direction, the spectrum, also the flavor, and this make us give us the possibility to do also astronomy with neutrino and astrophysics especially. It is something that I remember more than 10 years ago was something that was kind of difficult to imagine, or somehow to understand how we would have been arrived at this moment. But the thing is that we start to have enough information to do really physics of the sources and describe more in detail the sources, of course connecting neutrino with other messenger. But it's an important step that when we arrive to give some information more that you cannot catch with other messenger. That's to me an important step. That is something that allows us to do, that we can do also astrophysics with neutrino. So just looking at our galaxy, so looking very close to the Milky Way, that's where we have a different kind of emitters, like point-like emitters. We have also a diffuse component that we know that is produced in the galaxy, and so it's one of the main target also of neutrino telescope, since it is close, since we have a different observation on different bands, and then we want to understand something more about the point-like component that we have, and also about the diffuse one that is somehow related to the cosmic rays diffusion, and that we have this transport of cosmic rays inside of the galaxy, and also connected to the distribution of the gas that we have in our galaxy. And as you see here, I just reported the galactic plane observed for known point-like sources observed by Oak and S. So those are very luminous sources, TeV and gamma rays. And at the moment, when we look at the neutrino sky, so the different sample, and especially when you are looking to the track-like events that are the one that give us more opportunity to trace the sources and to look into the detail of the position of the sources, because we have more angular resolution. And then at the moment, we cannot claim at the moment that we have some excess that is so significant for the known point-like sources. This means that can mean that the component that we see in gamma is mostly related to the electron population, so basically to the leptonic part. Or also, if in the case when the hadronic, where we have an hadronic component, possibly we have also a possibility that the proton already escaped from the source region, because they escape before the electrons. And so maybe we don't have also the connection in position between the source, the pevatron sources, who is able to accelerate cosmic rays out to PeV, and the position of the source. So that's two possibilities that should be taken into account when we look to the point-like neutrino emission in the galaxy. And then when we look to the diffuse component, so here, as I said before, we have this component that is reported. In this case, here is the spectrum expected from our galaxy, considering all the gas distribution in the galaxy, considering all the physics of cosmic rays, so the cosmic ray transport, also the variability of cosmic ray transport along the longitude of the galaxy. And also this measurement here is tuned with the Fermi-Lat observation of the diffuse component, with the local cosmic rays measurements, and also with the very energy gamma ray recently observed by Lazo and Tibet. So putting all of this information together, we have a map of the expected neutrino, and we can look to this map also with the experiment. For example, we did this with IceCube, but with Antares too, and we observed that basically when we do this kind of template fitting, so looking exactly at the morphology or where we expect neutrino production in our galaxy, we can put a limit on this. So we have a template that is energy dependent, because as I told you, the spectrum of the cosmic ray is not homogeneous along the galactic longitude, so depending on the galactocentric distances. And also we have the morphological distribution, because we know how the gas is distributed in our galaxy. And this is at the level of less than 10% of the total flux observed by IceCube in the fuel sky. So we know that our galaxy, the diffuse component, cannot contribute to more than this when we look to the entire flux observed by IceCube. So here basically you have the spectrum, and here the two different set of IceCube looking at track-like events and looking at the AS, so high energy starting event. Two different samples. One comprises shower and track, the other comprises only track-like events. And in this case, we have the spectrum of the galaxy considering two different cutoff for the cosmic ray protons. So in one case, 50 PV, the other 5 PV. Here, the last result on this that we just obtained at the end of last year, we did an update of the model. So you see here the green and the red light give us the two possibility, the maximal and the minimal possibility of emission from the galaxy. That comes from an update of Fermi-Lat data, an update of the cosmic rays observation, and the fact that we have also observation by Lazo and Tibet that tune the model at very high energy in gamma rays. But still, we are at the same level of emission respect to the diffuse flux. So just now moving to the to the extragalactic component. So, okay, moving just 1 second. So moving to the extragalactic component, there was different stacking analysis by the ASPIC collaboration and also by Antares, of course, in the last year. And when you do stacking, you take into account also the position of the source that you are considering, and of course you are targeting the source that you think that can be responsible of the emission. In this case, targeting the blazar, for example, in this case with the 2-lakh catalog that was in a 2007 analysis, and this targeting of these known sources give an upper limit that is between around 20% of the total flux observed by IceCube. Then after this, it was other stacking analyses were done in IceCube. For example, those are reported. The one also this in the last year that was done last year by IceCube, just looking not only to the high energy gamma ray blazar, but also to the low energy. So in this case, they use the FLA catalog. And just putting, just considering the stacking analysis with this, the limit goes much below, and in this case, it's at the level of 1% of the total flux of muonic neutrino and antineutrino. So that's another hint that possibly this blazar, because some people claim that we cannot look just at the gamma ray, at the high energy gamma ray, because basically we can have some opacity and absorption. So we can also try the connection with the low gamma rays, but also in this case, the connection seems not not promising are the people were expecting. So we can have also the sketch when I put the different spectral point observed by IceCube, and the fact that basically when we do hadronic and photodronic production, so where we have acceleration of protons and interaction of the proton with the gas and with the photons in the sources, they are naturally connected to the spectrum on this way. So basically the accelerator pointing more at higher energy just because of the energy of the target. So the photons that we have as a target in the sources, so the one that are produced by synchrotron component in most of the cases. And also the low energy part that is more naturally explained through a reservoir of cosmic rays. So basically where you have star forming, starburst galaxy, and other kind of AGN, for example, or low luminosity AGN that have this possibility of doing proton-proton interaction. And so that's more naturally explained in this way. And of course, also the galactic component that goes in this part of the spectrum. Here, just moving to the starburst study, in this case, it starts basically to attract the attention of the people of neutrino, when in 2020, it was a first claim of a first small excess from the position of NGC 1068, and the fact that the people were looking to the possible starburst component and also connecting the fact that these sources have different really components. So we have also an AGN, we have a multi-zone emission on the AGN. And so it's important to consider all these regions where we have a neutrino production and see which of these regions can be really related to the measured spectrum of IceCube. In this case, it's a spectrum that goes from few TeV up to tens of TeV. So it's a low energy for IceCube in this case. And I will go into detail after a small introduction on the starburst analysis that I did with a group and my colleagues that I presented at the beginning of the presentation. So those sources are very interesting because they are very abundant in the universe. Actually, we have a magnetic field that is enough to have a production and containment of cosmic rays inside of the central part of this kind of galaxy. And it's a specific phase in the life of a galaxy that can last for more than 100 mega years. And so the only problem is that they are not very brilliant in gamma rays. So there's somehow it makes us some low constraints somehow on the physics of these sources, because generally we are looking to the gamma ray, especially for reservoir, to have more constraint on the physics of the sources. And then when we do the diffuse component of this kind of population, we should take into account also what is called the extragalactic gamma ray background measured by Fermilab. And so you see here different components that can be related to radio galaxy, to the one of the star forming galaxy, and what it was done into major work in 2016 and 2017 by Lisanti and Ackerman. It was that basically you have a dominance in this flux that's related to the blazar, and this dominance moved from 70% up to 86% of the total extragalactic gamma ray background measured by Fermilab. So that's it's abound in the study of starburst. And then we should look also at the physical cosmic rays inside of the starburst. So we have an equation that describes the cosmic ray transport. So when we have advection, diffusion, and losses of energy, and using just a leaky box model and some parameter like the maximal energy produced inside of a starburst core, the alpha spectrum and the rate of supernovae, we are able to modeling this emission that we have, just consider this hadronic production. So basically, mostly to proton-proton interaction. So this contain cosmic rays inside of the core of the starburst, where the T losses is greater than the escaping time. And basically, we can, through the observation by Fermi and to the Cherenkov telescope, we are able to modeling the physics and try to understand how can be the neutrino emission. In this case, also looking at the 11 starbursts close by observed and resolved by Fermilab, we look at the different spectral index distribution of the sources, and we see that basically, when you look at the diffuse gamma ray component, this is basically we try to do this kind of exercise. Before, there was the people were taking M82 as a prototype because it's a close by, very well known. The exercise we did is that to take into account not only M82 but all the 11 resolved starbursts by Fermilab and see how the physics can change considering all these 11 starbursts, and how can change also the neutrino production. In this case, we see that the gamma ray is not changing too much with respect to the prototype that we have before, so the prototype scenario. But when we look at the neutrino, this was the prototype scenario here, and you see here that the production of neutrino increased too much. So it starts to become non-negligible actually, and important when you look to all the diffuse component in neutrinos. And basically, as I said, at the low energy, basically we have the same as the prototype scenario. When we look at 100 TeV, we are increasing too much the percentage of neutrino related to the starburst. And also at the same time, we are leaving space in the high energy part of the set of IceCube to having other components. So for the accelerator and other type of neutrino production, so the sources that can produce neutrino also to photodronic mainly production. And so here in the multi-messenger study we did for the gamma ray diffuse component, we take into account the starburst, blazar population, and radio galaxy. For neutrino, we just do an interplay between starburst and blazar, and we consider also the bound on the Fermilab diffuse extragalactic background, referring to the Lisanti work of 2016. So having this prior in the study and using the parameter that I showed you before, we are able to obtain which should be the percentage of neutrino related to starburst when we look to the diffuse sky. And so looking at the two different samples, in this case for neutrino, the 7.5 year of high energy starting event and the 6 year of cascade events. And in this case, you see here that you have the 1 sigma set possibility for the starburst, actually an important component of the diffuse flux. So you have here the spectral point of IceCube. You can see that you can really explain a big part of the low energy spectrum through this starburst component. And that's the same also when you consider the cascade sample. And it's important in this plot that when the people were using the prototype scenario, you see here the maximal energy reached by accelerator or inside of the core of this galaxy, so inside of the starburst. Just through the prototype was impossible to confine the 1 sigma into sigma region, where we have here the maximal energy as a function of the percentage of the flux observed by IceCube. And when you took into account all these 11 and the distribution of spectral indexes that you have, considering all this sample of starburst, you see that we were able to confine this region. And so putting a limit at 1 sigma, that is up to 30% of, actually at 2 sigma we arrive also at 40% of the total IceCube emission. And also we are confining the region of the Pmax. So the maximal energy that accelerator inside of the core of the starburst can reach. So we are at the level of tens of TeV. And that's also another important information that should be also compared to what we have in our galaxy, because also we have a bound in our galaxy for the Pmax that come in between the knee and we have this bound related to different observatory of cosmic rays at Earth. And then we look also to the point-like component that we have basically considering the starbursts that are observed by Fermilab, and we see if this point-like component somehow can be observed through neutrino. And we take into account the bound that's come from the basically the infrared observation that tell us the star formation level that we have in this galaxy. And then, of course, we connect the supernova, of course, the interstellar medium to the star formation rate. And of course, with this information, we see if the model that we have saturating the gamma ray emission is still in accordance with the observation in infrared. That's important because we are not pushing too much. We cannot push too much the possible emission in gamma rays if we exceed what is the infrared observation of these sources that tell us how much target we have inside of these sources, basically. And this is the case for these 11 sources observed by Fermilab. So all of them are starbursts, and some of them have also an AGN inside. So it's interesting to look also to the interplay between these two components. And here, when we obtain the normalization of the starburst respect to the sensitivity of KM3net, that is the telescope that we are building now in the Mediterranean Sea, and also the sensitivity for IceCube Gen 1 and Gen 2. And basically, here we have also expert in KM3net and this sensitivity. And see, you can see that we have some interesting sources for these telescopes. Basically, the small Magellanic Cloud, the Circinus, are really close to what KM3net can observe in 5-6 years of observation. And another interesting point is NGC 1068 that was claimed like before at the winter time, that it was the first, the major hotspot in the northern sky of IceCube. And interestingly, we see how, just considering the starburst component, we are a bit far from what is the sensitivity of IceCube. So it's this gives us a suggestion that it's important to consider in this galaxy, not just the starburst component, but also the other component related to the hosted AGN. So, and in this case, to understand, I reported also this slide to see that it's important for the future, having also much more observation at very energy gamma rays, especially from CTA north and south. In this case, I divided the sample of starbursts observed by Fermilab in the northern and southern sky. And you see that this information will be crucial because it's through that information that basically we are constraining the physics inside of the core of the starburst. So this will tell us much more, and that can make also a difference in the prediction, where we are extrapolating this prediction to the very deep sky up to higher redshifts. So that's an important information that will comes to the. And then let's start to concentrate a bit on NGC 1068 that was claimed as this big hotspot observed by IceCube, and it was a 4.2 sigma excess. And basically the excess was observed in the low energy part of IceCube sensitivity. So basically in the TV energy region, and this was done through the track-like events collected between 2011 and 2020 by IceCube collaboration. So it's very interesting because it's a close by Cepheid galaxy, and it's a distance of about 14 megaparsec. The luminosity of the, so basically, as I said before, these sources have a starburst component, so an high star formation rate in the core, they have an AGN, they have a jet that was resolved by ALMA and VHE. And also it's important because we know basically we are able to constrain as should be the star formation rate in the central part. And so interesting to do an interplay between this component and see which one can do a better estimation of neutrino emission, and basically which one can account for the observation made by IceCube. So here I reported observation in different bands, and as I said before, the the jet observed is at the level of the kiloparsec, so it's a kiloparsec extension. And I will tell you after we have also some knots inside of this jet that we will take into account. So here again, the spectral measurement made by iScope about the sources. So you can see here the spectral index made by, so this one that is between 3.2, 3.3, the spectral index, the normalization measured by iScopes with the track-like events. And you see here the electromagnetic part observed and the difference with the observation of Fermilab. So the main point that the people start to consider is the fact that we have this level of flux when you are looking to the Fermilab emission between 0.1 to 100 GeV. And this level of the flux, so the normalization of the differential flux that you have when you look to the spectrum measured by iScope. So it's a kind about of 2 orders of magnitude. So the people start to think to this fact and say that somehow the sources maybe have an opaqueness region for the gamma ray. So maybe gamma ray should be where you have a hadronic and photodronic production, you are producing at the same time neutrino and photons. So basically, if you observe TeV neutrino, you have something at the same level that should be observed in gamma ray if you don't have any absorption. So in this case, you have absorption in basically in gamma ray. There is different observation on Fermilab, but having this kind of flux on neutrino, you should assume that somehow you can have absorption, and this allows you to make some scenario where you explain neutrino and at the same time you explain the electromagnetic observation. And basically, as I told you before, there is different component. The different component can have a photodronic production through the interaction of proton with photons, so with the production of neutrino through the lambda resonance, and to the multi-pion production is the 2 main components when you have a photodronic interaction. And also what we call hadronic interaction, where you have a proton interacting with a nucleon, with an hadron basically, and you are producing also, in this case, positive charged pion and neutral pion, and therefore also a neutrino and photon gamma rays. And you can see here that you have basically what is called hot corona. I call it here hot corona. It was a model built by Murase et al. A couple of years ago, where they considered the emission from the inner part of this AGN, so from the hot corona, and the interaction of the cosmic rays produced in this region with the dusty torus. So with the region of the torus where you have a lot of dust, and so where you can have proton-proton interaction. But also in the hot corona, you have also photodronic, where you interact also with the infrared photons, and you have also other components like that we'll go through fast in this talk, the ultra fast outflow, and that can have also what is called UFO, that can have a photodronic and hadronic interaction. For the jet component, we have at the moment we consider just the photodronic production. But basically, for the future, maybe we can also think about the hadronic and proton-proton interaction if we have enough material to be considered there. And also, of course, for the starburst component, we just have the proton-proton interaction because come from the central part of this galaxy where you have a lot of star formation rate and a lot of gas to be used as a target. And you see here, looking in the detail, that basically this is the spectrum at 1 sigma produced by NGC 1068, just considering the starburst component, just consider the central 100 parsec of the sources, and considering the physical cosmic rays inside of this core, and looking to the amount of gas or material that we have there, and the maximal production of neutrino that you can have. So basically, this is bound by the luminosity that you have from the sources, of course, and the fact that you have a cutoff at 100 of TeV, because it's also a bound that comes from the gamma ray observation. And you see that just considering this component, you are very far from the iScope butterfly. So you are at the level of less than %. So we cannot say that just the starburst component in this case is not enough to explain this kind of flux. And then coming back to this hot corona, as I told you before, we have a possibility to accelerating proton in this region. So here, magnetic field of 100 of Gauss are considered there. And then you have a possibility that this outflow goes and arrive to this outer region where you have basically this dusty torus, and you have this proton-proton interaction. As I told you, you can have also proton-photon interaction. And basically what comes out is that from this work of Inoue and Morazet last year, you have they are able somehow to justify all the electromagnetic part, not all, part of the electromagnetic spectrum, and saturate basically all the ice cube observation with this component. Somehow it starts to become tricky in this case because it's necessary for them to considering multi-component related to this hot corona to explain all the electromagnetic spectrum. I think that start to be tricky, and it's a lot of you have to make a lot of assumption for this that we should understand if they are physically if somehow we have some constraint that can tell us that they are physically possible or not, basically. So that's an important point. But I should say that if you added this component, of course, you are solving this problem, and you are going up to the sensitivity of ice cube, and of course you are explaining most of the neutrino observed by ice cube that are actually 79 events. Actually, we should take into account that between these 79 events, we also atmospheric, of course, an atmospheric contribution, but as I told you before, the excess was at the level of 4.2 sigma. And so another scenario that comes out at the beginning of this year, the fact that we have this ultra fast outflow that are basically related to the wind that you have when you have a black hole. So you have basically like a stellar wind, you have an inner wind termination shock, you have a discontinuity, and you have an outer forward shock. So in this case, you can explain. Also, in the previous case of corona, we are at the level of few Schwarzschild radius around the supermassive black hole. Here we arrive up to 100 of Schwarzschild radius, so we arrive up to tens of parsec around the supermassive black holes. And so through this upstream and downstream region, you are able to accelerate cosmic rays up to PeV energy, and basically that's the hadronic production that you have through P gamma and PP interaction. So basically, you see here the photon that you are producing through proton-proton, and you see here the neutrino that you are producing through P gamma. So basically, they are concentrating in this case just to high energy part, so the part observed by Fermi-Lat, and the upper limit observed by MAGIC. So you see here that basically you have the neutrino component that come from PP here, and the neutrino component that come from P gamma. So you see the two. We should say that also PP generally in the sources is a more efficient production, just because of the cross section that you have with respect to the P gamma. And you see here still how far you are from the spectrum measured by ice cube. So going up with this presentation, we were discussing last year, actually, Paula told me that, look, these sources have also a jet. So I give a look at the jet of these sources, and I see that last year a paper comes up explaining how basically the different region of these sources are resolved through ALMA, and basically there is different knots in the head of this jet that is a kiloparsec jet. And it's at the moment I estimate I use it as an emitting power, something that is a bit updated, but maybe we will have soon a new updating on the luminosity calculation and the power emission from the total jet component and the different knots component. And so you see here the different knots, the 4 knots that are the dimension of 5 parsec more or less. And inside of these knots, we used just a recent code that calls AGN pi that allow us through the assumption of an electron population inside of the knots moving fast inside of the jet. So we are able to modeling the leptonic emission of the electron inside of the knots and see how they are fitting well with the data that we have. So here I just made the two examples considering a magnetic field of 900 microgauss and a magnetic field of 1000 microgauss. Those are very preliminary plots. And we see that assuming this, we are able somehow to explain the part of the ALMA and VLA observation. Somehow we are below the bounds of Fermilat, and we are also respecting the magic upper limit. So those give us an important bound whenever we want to build a leptodronic model. Why I'm saying this? Because we are using the lepton to producing the photons, so synchrotron photons, and those photons will be the target for the protons that are accelerated. In this case, we have two possibilities: that the proton are co-accelerating inside the knots, or the proton can be accelerated in the jet. So we have these two possibilities, but in any case, the target is come from the synchrotron. So that's the reason why I call this leptodronic model. And here it's interesting because taking into account, so here it was the just concentrating on the energy part of the spectrum. So we see here that we are that's basically the blue one is the expectation that we have from the starburst component of the sources, and you can see here in the orange one the expectation that we have in orange. And when we put together these two components, we are still fitting well the observation of Fermilat, and we are still below the bound of magic. So that's important because that's we know that from we are considering we have a good estimation of the target for the photonic production, and basically we are not exceeding this bound. And I will say that, of course, if we are considering the other component like the hot corona or the AGN wind outflow, basically introducing the other, we are a bit exceeding what is the bound that we have here. So some of this component is not so high how it was described in the literature. So some of this component should be below to the description, or we have some component is extremely dominant and the other that are really subdominant in respect to what we observe. So that's a possibility. And so here, and then after the leptonic, we built with my collaborators the photodronic production. So we follow what is the photodronic production. In this case, we start with a work with building a structure that was made at the beginning by Muras in 2014. So we follow this structure for the photodronic production, and then we will go through Aroyan and Kern in 2008 in the near future, because in this building production we have basically the neutrino produced by the lambda resonance, but we need to take into account also the multiplying production. So until a certain energy, most of the neutrino are produced by the lambda resonance. When you are exceeding this energy range, you have also a multiplying component that becomes important. And here you see adding together so basically before we do leptonic production for each of these knots, and we add all of them together. And then we do we did the two different cases, the acceleration of proton inside of the knots and the interaction with the synchrotron photon inside of the knots, and the acceleration of the proton in the jet and the interaction of the photons that are produced inside of the knot by the electron. So we have these two possibilities. And both of them, of course, are in agreement with the electromagnetic bound. So with the ALMA from one side, from the Fermilat, and to the magic to the other side. And so you can see here how, considering the two different cases, so proton co-accelerated in the knots, you are producing this kind of spectrum. Proton accelerated in the jet, you are producing this kind of spectrum. Here, in this case, it's we assume a very high level, in this case, an intermediate level of efficiency for the photodronic production. We will go into this more in detail. So for this reason, it's very preliminary, this plot, because it's we should check the efficiency of photodronic production for this specific case. So it's something that we will do better in the future and the near future. And here I put a plot where I put together the starburst component and the one that comes from the jet. In this case, I assume a very high photochromic efficiency. So it's something that, to me, yes, is kind of can be kind of an upper limit for the production that we have. This one, unless we have some injection more of power inside of the jets that we are observing for some reason. And you see here that in the case of the knots co-acceleration, the level of production is very low. In the case of the entire jet, it's increasing a bit, but we are still at the level of percent with respect to the ice cube observation. So it's something that we will go into the detail in the near future, that it deserves to go into the detail, because we want to know basically if this is correct or not, and this is a bit higher or lower. In any case, maybe can be in the range of observability of ultra energy neutrinos, so radio detection that we have there, that we are building now also in the Earth, different radio detection telescopes. And so we want to understand if through neutrino, we can understand something better about the jet of these sources. And going through this, I want to say that maybe a way to disentangle, so I told you that, so these different zones of emission are really difficult to disentangle, especially neutrino. The only way to try to disentangle is to put in together the different messenger and the magnetic spectrum. And somehow, when we look to the neutrino, for some of these components, we expect some kind of variability, like for the jet, for example, or for the wind. For other, we do not expect any variability, like for the starburst component, or maybe also for the corona. It should be investigated more in detail. And this is the work done by IceCube in 2019 that show a first neutrino light curve. I really like too much this work, because whenever we will be able to produce also light curve with neutrino, with TV neutrino, we will say something more about the physics, because it's also a matter of discrimination of different models, also the time constraint on the emission. And this is important because maybe we will reach also a smaller binning, also with CampNet, I really hope. And this will allow us to really do a more concrete astrophysics with some targeting sources that are close by that we know. So maybe also the variability can be a matter of discrimination between the different zones of emission of LTC 1068. And then I want to finish the last slide with something that I was just considering in these last days. And I was talking today actually about this with Paolo, that basically this is the distribution of the star formation rate that we have in the universe. And you see here that are peaking mostly in the at zeta more or less equal 1. And basically, when I say that whenever you have, for example, a Seifert or low luminosity AGN, where basically you are the interplay between these two components, so starburst from the one side and AGN multi-zone emission from the other side, and you have basically after the switch off of the starburst activity, you can have the AGN component that stay there for longer time, that's a fraction of giga years. And basically, what I was discussing that whenever we are moving in this direction, basically, if we are targeting the point like galaxy where we know that there is a starburst component and AGN component, basically, maybe we are forced to consider the fact that it's the AGN component start to be the dominant one, and the starburst component, of course, is the less dominant one. And this is a different case where you are inside of this energy range, because it's exactly the period where you have a maximum of star formation rate, and when you are producing much more neutrino through this process. So basically, as I told you before, the starburst component becomes very important when you look at the diffuse sky. So basically integrating up to, as we did in our work, integrating up to redshift above 4. But when we look to the single sources close by that are presenting these two different components, basically, most probably the AGN related component are the dominant one in this case. And just okay, sorry, finishing that's it's so that's the spectrum of iSCOOP with the different neutrinos, so with the NUMU and with the neutrino tau. And you see here basically the comparison within the flux with the set measured by NGC 1068 and the set measured by TXS 0506. So at least we know that we have if we believe that this is really the spectrum emitted by the sources, at least we know that we have a different component to describe the different spectrum that we measured in the full sky. So here another sketch where I put together the future of neutrino astronomy, where I say that we will go ahead with iSCOOP Gen 2 in the Mediterranean part. Antares was just finishing last year with more than 12 years of data taking, and ChemTriNet is ongoing. We have at the moment like 21 strings that are taking data. We will reach the final configuration in 4 years from now, and basically putting together ChemTriNet, Antares, and iSCOOP and other observatory like P1 and Baikal GVD. We will able to do really astrophysics in the sense that we will reach enough statistics of the events to targeting specific sources and to characterize better the full sky spectrum. So we will be able to do this too. So the summary and the astrophysical neutrino flux observed by iSCOOP favor a multi-component scenario, so different astrophysical population that can account for the different energy section. And then a considerable amount, so from 40 to 50% can be related to what we call the reservoir. So the reservoir of cosmic rays like the galactic that is up to 10%, most of the other reservoir like star-forming starburst that we consider. The diffuse blazar seems to be subdominant to the measured flux of iSCOOP, but this depends, it's still related to the sample of neutrino and to the stacking analysis done and to the assumption done in the spectral indices. So this is something that will improve soon also in the future. For the case of NGC 1068, we have, as I told you, we have a different component like the hot corona emission, the outflow emission, and those seems to be the major factory of neutrino that we observe. Actually, the hot corona it give a greater flux. The neutrino light curve maybe will be used as a disentangling this possibility in the future. And with the time-dependent analysis will become also more effective whenever we have the global neutrino network operative, so where we have all these telescope operative together, because we need more statistics for doing this and decreasing the time being that we need for doing astrophysics with a specific target. So that's all. Thank you.
Thanks. Very interesting. Do you have any questions?
Yes. I was wondering what type of neutrino variability do you expect?
Yes. Yes. Yeah. Actually, it's an interesting question. Basically, you know, from starburst component, we don't basically expect such a variability in this. You know, that's you have a factor insignificance, a factor 3. So it's a big increasing in the measured flux. This kind of so if you have we don't expect such a variability in the flux in the starburst in any time window. Basically, I think that in the AGN wind and the AGN jet, yes. So I think that we can expect such a level of variability in the flux that will arrive on Earth. And the time window, of course, I think that we know that for knots that are at this level, we would be nice to have, like, I would say, weekly and daily. We will never have a daily time beam, but will be maybe interesting. But maybe also at least reaching monthly time beam maybe will be interesting, because for sure we can put some constraint on the region. So
Yeah.
this I think that this can be something interesting for the future.
Indeed, I was thinking that you decided to explore the blob in because you have this information from the variability.
Yes.
So that can be
Yes.
some upper limit
Yes,
on the
exactly.
dimension.
On the
of the-
limit, yes.
Okay. Any other questions? Dai.
Sorry, there is one more question from
Okay.
remote because there was raise hand here from Antonio Stamerra.
Yes.
Ciao.
Just please.
Can you hear me?
Yes.
Yes. Ciao,
Hi,
Antonio.
good morning. Ciao, Antonio. How do you do? Okay, it was a pleasure to hear this and also this. I think your talk also highlighted the importance of having this multi-messenger, also the understanding, the astrophysical understanding of the object. Anyhow, regarding this slide that you are showing right now, I am a bit puzzled by the claim of variability. When I saw this one, sorry, there is someone's ringing. But when I saw this one first, I also asked, but they said that this is cannot be a claim of variability. First of all, because this is a 3 sigma pre-trial.
Yes.
And also maybe only M87 has some hint, but so let's say the claim of variability to understand the jet is a bit too strong, maybe.
Yes, I agree with you. I just put this slide because I think it's a first work that goes in this direction. So as I told in my final talk, whenever we have a global neutrino network, maybe we'll have enough statistics to really look at something that looks like a real light curve. In this case, of course, it's as you said, it can be considered a fluctuation of the background unless you reach 3 sigma. So, but I reported this because to me it was interesting because it's the first work that goes in this direction of try to looking in this direction basically. Yes. But I agree with you. We cannot take this as a as a strong claim of variability for each of these sources.
Yeah, thanks, Antonio. The other small question, maybe you gave a lot of information, but one of the problems we are facing with the gamma rays is that, and Cherenkov telescope, is that we do not see anything. And so you also pointed out the magic result we got on 1068.
Yeah.
And actually, this is a problem. And so I don't know if, assuming the neutrino emission comes from the jet, this can be solved. I mean, because it means it clearly what is going out in the last years is that it's clear that the gamma ray emission is absorbed.
Mm-hmm.
Yes, so I don't know.
But
yeah, please.
Yes. So gamma ray is absorbed because up to now the people were considering the central region. So in the case of UFO or of the hot corona, you were considering the under Schwarzschild radius. So you are moving up to 10 of the parsec from the central core. In the case of the jet, you are going up to a kiloparsec scale. So basically, what we can expect is that. So for this reason, I say that we use the electromagnetic part to try somehow to see if this is too far from the gamma ray observation or if it is in accordance with this. Because in the case of the jet, especially from these knots that are at the head of the jet, you can have this kind of observation because you are not very close to the absorbing part that you have in the other component.
Okay, thanks. Grazie, Antonio. Ciao.
No, grazie a te. Okay, ciao.
Have a question here?
Very interesting talk. Thank you, because I found very interesting the approach of using, for example, my main expertise is the infrared
Yes.
density.
Yes.
So I would like to understand a bit more how we use this to derive the
Yes.
Because
we go basically mostly with the Kenny-Katz relation where we take it where we are associating the infrared to the interstellar medium and supernovae and supernovae rate. So all the amount of gas that is there the infrared give us an important bound in this sense for us. Yes, and it's important because it's the target. So if we cannot, for example, if we try to saturate the gamma rays, assuming that all of this is atomic production, and these need a target that is, for example, I don't know, order of magnitude between of difference from what we observe in infrared, that could be a problem. So
but when you use the say the star formation rate function, the Schechter function,
yeah,
you derive the contribution of the whole population.
yes, this when we extend it to the then when we do so I was talking before for the point like component. So when we do to the deep sky and we extrapolate to the Schechter function, in this case, yes, we use the known function.
So you use the connection between the infrared and the neutrino and the gamma rays from single objects, and you
Extrapolating to the deep sky. Yes,
okay.
yes.
Other questions? If there are no questions, we can. Sai cosa mi sono chiesta, che però non facevo la domanda, quando ti